Since we had started this review, we'll quickly go over a few slides regarding what we have done. So if you guys recall, this is the picture that I had at the end of the last lecture. We said that after studying one particular amplifier in detail, which was this particular one, common emitter, the simple common emitter amplifier, we looked at several problems that this particular stage has. And as a result of an attempt to solve some of those problems, we generated various possibilities. And among the possibilities was, one of them was a common base amplifier. We said, what if we apply an input instead of at the base, we apply it at the emitter here, and take output at the collector here. And we saw interesting properties. Gain it is capable of giving same gain as common emitter. Output resistances are similar. Input resistance is very small. And as a comparison between the common emitter and common base, we said that in terms of the ability to provide gain, input and output resistance, a common emitter is better than common base by a factor of beta. So something would be much better in common emitter amplifier. Either the gain would be much better, or the input resistance or the output resistance by a factor of beta. So that's there. But we also saw some applications of lower input resistance. But the main motivation for going towards common base was not the gain and the output resistance, but was the fact that there is no coupling capacitor between the input and the output node, and that was the motivation, that maybe Miller's effect would be absent there, and we would get very high bandwidth here. But what we had seen was that you get high bandwidth only when you drive your common base amplifier through a large source resistance, resulting in an effective large emitter resistance. So whenever emitter resistance is large here, effective emitter resistance is large, then you end up with a high bandwidth. But when you attach a large resistor, we saw that results in very low value of gain. So as an attempt to take advantage of common base amplifier, and a strategy was thought of, that common base amplifier works best when you drive it, as I said, through a large resistance. Large resistance means effectively a current source. And so the strategy was, take a common emitter amplifier, use it to convert a voltage to current, and use that current to drive a common base amplifier. And that resulted in the Cascode amplifier that you see here. So Cascode amplifier has similar voltage gain, output resistance, input resistance as a common emitter, much improved upper cutoff frequency, and reduced sensitivity to upper cutoff frequency to increase in voltage gain here. And the key point here is that, which we forget, that when we look at the common emitter part here, the gain here at this particular point is same as common emitter, but the gain at this point here, because you're looking into the emitter, the gain at this point is very small, and therefore all this C mu and which was getting multiplied by the gain gets only multiplied by gain, which is only 1. So Miller's effect is drastically reduced, and so that's the advantage of the Cascode amplifier. Another of the problem was that at various places we require higher input resistance, lower output resistance, and managing that using a common emitter amplifier is difficult, because you want gain also from a common emitter amplifier. And if you demand simultaneously large input or small output resistance, it becomes difficult. So we saw that a stage like this can be very useful. A stage which doesn't provide you gain, doesn't specialize in gain, but it specializes in high input resistance and low output resistance. And the other benefit that we'll see is that it has higher bandwidth. So wherever you have a problem with input resistance, or you have a problem with output resistance, you take this particular stage and insert it. And so gain is very close to 1. And we also saw that input and output resistance, its ability to provide high input resistance and low output resistance, is much better than what you can get from a common emitter. Even if you try to get a high input resistance and output resistance through a common emitter, you can't match the capability of the common collector amplifier. All right, so it's a very good stage in terms of, we also call it a impedance transformer. If you look at when you look at common collector from the input side, you see high input impedance. And when you look at it from the output side, you see low impedance. So it's an impedance transformer. It takes a high input impedance, converts it into low output impedance here. Okay. So, that's why I'm saying wherever matching is required, you have to drive a very low impedance load here, and the input has a sufficient sufficient source resistance. So what you do is you insert a common collector amplifier, which will match the load resistance to the output resistance here. Anyway, so besides the gain input and output resistance, because many times this amplifier is used at the output stage, the swing is important. So one needs to understand what are the limiting factors on the swing, and one of them is the biasing current. The biasing current really limits how large a swing you can get. The ICQ times RE parallel RL tells you how large you get. Besides the fact, if there is an upper limit on how large the input can be, if the input cannot exceed the supply voltage, then you get this limit also, VCC minus VB here. And so that brings us, again, this software always, flips the current. I don't know why. So the current is down, okay? The current is down here. So a much better biasing, if you do want to use a common collector amplifier, use it with a current source. Because with the current source, you can use a much lower current to get a swing that you really want. From the other amplifier, you would require a much higher current here. Okay. The efficiency of this particular amplifier is low, but it can approach close to 20-25%, while the other one is very low efficiency there. All right. So a much better biasing, most of the time you would see a common collector amplifier being used with a current source here. And the other point that I was making was that it is a high bandwidth amplifier. In many cases, what happens is that the dominant pole, which determines the frequency response of most of the amplifiers, the dominant pole is cancelled by a 0 here, and as a result, the non-dominant pole becomes the deciding factor. Okay, and the non-dominant pole, which means a pole at much higher frequency, so the bandwidth here becomes much higher here. So for all the amplifiers that we have seen, common emitter, common base, and common collector, the highest bandwidth that you get is from this particular stage, common collector stage. All right, so with the common collector, you can use it as an output stage, but it's not very efficient. And therefore, a much better stage that we saw was a class B. And in an attempt to solve the crossover distortion associated with class B, we said the class AB is a much better stage. And the basic idea from which we this particular circuit evolved was that an efficient amplifier should take power from the supply only when power is delivered to the load. It's a basic principle that you should take power only when you're delivering to the load. And starting from that, we built the common base, class B, and we added the diodes to keep these transistors at the edge of conduction, and then we get an amplifier which is reasonably. This is an upper limit. This kind of an efficiency you get only for class B. But in class AB, you allow some current to flow here, so efficiency does not reach this particular value, and it's a little lower than that. Depending on at what current do you bias these, at what current these are biased, so one has to look at the biasing currents of QN and QP and these transistors, these diodes here, and on that basis, then calculate how much is the loss compared to this upper limit here. And note also the upper limit on efficiency you always reach when you drive your amplifier to the maximum extent possible. When you drive VOP, so you apply input such that V0 goes right up to very close to VCC. It's only then that you get high efficiency, very high efficiency. If you're not using your amplifier to the fullest extent possible, if you're not driving it that hard, VOP is let's say VCC by 2, then the efficiency will of course be lower. Okay. So highest efficiency that we are talking about, the 78.5%, will only be reached at that limit, right? So I mean, you don't play your music systems at the highest possible volume, right? If you're not doing that, you're not reaping. So one benefit of loud music is you get the best efficiency, right? So you can always justify, why am I using it? Well, I'm using it I'm not wasting any power, right? I'm trying to get the highest efficiency. So that's your technical excuse for that. Active load is another interesting stage, a common emitter amplifier. So you take a resistance out and replace it by a transistor, and a very interesting stage allows you to get very high voltage gain without requiring very high supply voltage. All right. So and the gain you can see here is very stable also. The gain doesn't depend on the bias current. The gain, as you can see here, depends only on the early voltages of these two transistors and no dependence on bias voltage. There is a dependence on temperature, of course, through this VT term here. Okay. And the only problem with this particular stage, as I said, is biasing. Because the little bit of change here may cause this transistor or this transistor to go into saturation. So how do you adjust that? Well, it depends on the other stages that you connect to it. And so the stage here and the stage here may force this particular voltage to a stable point here. Then was the differential pair. Differential pair was, we arrived at differential pair through a route of building amplifiers without coupling or bypass capacitors. And this is what we ended up with. And although we arrived at through that particular route, differential amplifier is known for this property here, that it amplifies the difference of the two signals, besides the fact that it doesn't use coupling and bypass, and therefore it can amplify DC. It amplifies the difference of the two signals and rejects anything that is common here, right? So we have differential mode gain, which is high, and we have common mode gain, which is pretty low here. And the other differential pair is where you try to build high gain by replacing it with active load, and you try to make the common mode gain very low by replacing it by a current source here. So you end up with a very popular configuration, differential pair with current mirror load. And the gain, of course, is very high, but you build gain only at this particular point. At this point, if you look at it, the gain would be practically, well, calculate. Find out how much will be the gain at this particular point. All right. The gain here is given 0.5 GM R02 parallel R04. Another interesting thing is that although we couldn't calculate the common mode gain, but what is very interesting is we have two inputs. And if you look at this input here, this would try to create a voltage here, which is opposite in phase. Both the inputs, remember, in common mode, both the inputs are the same. So this would try to create a voltage here, which is opposite in phase with it. So let's say negative. This one will try to create a negative at this point, and this negative travels here, and this negative goes to the base here and tries to create a positive here. So what you get is a cancellation effect. This is trying to create a positive voltage at this particular node, and this one is trying to create a negative voltage at this particular node. And both the voltages are very close to each other. And so there's a cancellation effect of VIC that is taking place here because of this current mirror action. If I didn't have this current mirror, if I had an RC here and an RC here, this particular one does not directly affect this particular part. Okay, but now because of this, this goes and develops negative voltage here, this negative comes here and causes a positive voltage, while this one creates a negative here. So because of this cancellation effect, that our method of taking values of Norton's currents and Norton resistance and approximating it didn't work very well, because there's a cancellation effect going on, and you have to do the calculation very accurately. You can't make any of those approximations, and then only you'll get the right estimate for what the actual value of gain is. So what we can see here through the circuit is that common mode gain is going to be very low. But how low, as I said, well, you have to do an exact analysis to get that. And otherwise, of course, you have the simulation to give you the right answer here. All right, these were we said that these are the basic building blocks. These are the three primary colors, red, green, and blue. And three primary colors which you can combine to generate many different colors or different circuits here. And these are single transistor circuits. These are some of the transistor pairs that we encountered. And by connecting and combining them, you can generate a wide variety of circuits here. And two examples were that we saw at the end was this operational amplifier, one which did not use any active load, all resistive loads everywhere. So this is the one. And realize here, this is a place where I think some questions were raised. Where do I need a PNP transistor? And we saw that if you use an NPN differential pair, the only way you can add the next stage is through a PNP. A NPN stage did not give us any gain, right? So we saw the necessity of using PNP transistors right there here. Okay. So if this is NPN, this has to be PNP. On the other hand, if this were PNP, then these would have been NPN. Without that, you can't connect. So you get into that only because, remember, we have to take care of biasing besides the fact that we have to build up gain. If we had capacitors available to us, and then we could have isolated the biasing of this stage from this stage by separately biasing it. But we can't do that. In this case, these are all directly coupled. And so the biasing of this affects the biasing of this and affects the biasing of this. They're all coupled to each other. And so both, you can see the use of complementary transistors. And the other thing is, whenever you build a high gain amplifier, you have multiple poles and zeros. And many times we use negative feedback, but even if you don't use negative feedback, let's say you don't actually implement, but when you lay out your circuit, there may be a path from the output to the input that somehow this, through the ground or the power, the signal gets coupled from the output to the input. And what would happen is, even if you don't implement intentionally a feedback would exist through various other paths that are there sometimes. And what happens is a high gain amplifier tends to oscillate. It's unstable. And therefore, what you need to do is, you need to add a compensation capacitance. Whenever you build multi-stage amplifiers, you have to add a compensation capacitance to make it stable, to make sure that under the worst case feedback, my amplifier will not oscillate. So you have to take care of that. So this is a very, very important part here. The other one was where we try to build a more, a better amplifier in terms of gain and take advantage of a lot of concepts that we knew. So a differential pair with active load, a class AB stage, and also this kind of a NP-NP-NP pair to build up the input resistance of the stage here. All right. The other thing, so that's where we ended our course, formally ended operational amplifiers. The other thing, very important, is this methodology. At the end, if you're designing, analyzing, or whatever, besides the DC, you end up with a small signal circuit. And how do you analyze? We again and again, I've been emphasizing that use this technique here. Take your analysis to a higher level. Don't do it at the, as much as possible, don't do it at the hybrid pi level here. So take it to a higher level. And how do you take it to the higher level? Well, by recognizing that most circuits that you look at, they'll be made up of blocks like this here, a block like this, or a block like this, or a block like this. So you break it up into sub-blocks, and you already know the results of those sub-blocks. You already know the results. The results have been pre-derived, pre-verified. They are accurate, and so there are no chances of error. The error will only come through your memory. If you have not memorized it, if you have not used it very well, you may make an error there. But if you do that, then the chances of error drastically goes down. And so how do you apply this methodology, divide and reuse? How do you go about implementing it? One of the ways is that wherever you require gain, go ahead and build a Norton's equivalent. At that particular point, build a Norton's equivalent. If I want a gain at this particular point, build a Norton's equivalent. Norton's equivalent, if you note, it simplifies in two ways. One is, so Norton's equivalent will require you to find Norton's current. So when you calculate Norton's current, remember you'll short this. When you short this, everything below this short disappears in your entire circuit. So a large part of the circuit no longer matters because you've taken this particular node and you've shorted it. And so everything below here, all that thing no longer matters. It goes away. So you're only dealing with a fraction of the circuit when you calculate Norton's current here. And then once you look at Norton's current, then you go ahead and look at these. Basically, a stage like this, you look at here, 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 all these things you apply in a systematic manner to calculate what the Norton's current is. Okay, in this case, of course, is straightforward. The other thing is when you are calculating Norton's resistance at a particular node, then what you do is you remove the source. So when you remove the source, again, things simplify. When you remove the source, note that if I remove a source from a particular circuit here, then I'm only left with the resistor. So it again leads to simplification. All right. So a complex problem you solve by doing the analysis twice. Two different analyses. One analysis for Norton's current and one analysis for Norton's resistance. Instead of doing one big analysis, you break it up into, it's always a strategy. Whenever you have complexity, it's always a strategy to break a problem into smaller problems. And that's what we're doing. That instead of calculating the gain of the whole thing, you break it up into two parts. Norton's current and Norton's resistance. And then how do you calculate Norton's current? You further go ahead and break your circuit into these parts here. And you use the results of these parts, and then you stitch those results together, and you arrive at what is the Norton's current and what is the Norton's resistance here. When you look at Norton's resistance, generally you look at the upper half of the circuit, calculate what is R up, what is the lower half, R down. And in all of this, we said make approximations that R0 is much larger than R pi is much larger than 1 over GM. And make approximations as early as possible to keep your results manageable. And then, as I said, with this strategy, most of the analysis is straightforward. Okay?